Discover how shrinking gold to nanoscale transforms it from chemically inert to a powerful catalyst. When we shrink gold from bulk size to nanoscale, something remarkable happens. It transforms from being chemically lazy to incredibly reactive. Let's explore the fundamental question. Why does making something smaller change its chemical behavior? Bulk gold is one of the most chemically inert materials we know. It doesn't corrode, tarnish, or react with most substances. Chemical attacks bounce right off bulk gold. This is why gold jewelry lasts forever and why gold is used in electronics. However, shrink gold down to nanoparticles, and suddenly it becomes a powerful catalyst that can speed up many chemical reactions. Gold nanoparticles actively participate in reactions, breaking bonds and forming new products at impressive rates. The first reason for this transformation is dramatically increased surface area. The key metric is the surface-to-volume ratio. As particles get smaller, this ratio increases dramatically. For a sphere, the surface-to-volume ratio equals 3 divided by the radius. Notice this increases as radius decreases. Let's compare actual numbers for different sizes of gold particles. A 1 centimeter gold sphere has a surface-to-volume ratio of 0.3 per centimeter, but a 10 nanometer gold particle has a ratio 100 million times larger. This massive increase in surface area means many more gold atoms are exposed and available to participate in chemical reactions. But surface area alone doesn't explain everything. Quantum mechanics enters the picture. In bulk gold, electrons can move freely throughout the entire metal structure in what we call a continuous electron sea. Think of electrons as a sea that can flow throughout the entire bulk metal without restrictions. But in nanoparticles, electrons are confined to extremely small volumes, and quantum mechanics fundamentally changes their behavior. The energy levels become quantized, according to this particle, in a box equation, where energy depends on the confinement length, L. As the confinement length L decreases, the energy gaps between allowed electron states increase dramatically. Bulk gold has many closely spaced energy levels, but nanoparticles have widely separated discrete levels, fundamentally changing chemical reactivity. Another crucial factor is the coordination number, or how many neighbors each atom has. In bulk gold, each atom sits in a face-centered cubic structure, with 12 nearest neighbors surrounding it. Each central gold atom is stabilized by 12 neighbors, making it chemically satisfied and unreactive. But atoms on the surface of a nanoparticle have only 8 or 9 neighbors, leaving them with unsatisfied bonds. These unsatisfied surface atoms are chemically hungry and eager to react with other molecules. The fraction of atoms on the surface is approximately 4 times the atomic diameter divided by the particle diameter. For a 3 nanometer gold particle, roughly half of all atoms are surface atoms with unsatisfied coordination. The electronic structure of gold fundamentally changes at the nanoscale. You might wonder, why does electronic structure matter for chemical reactions? Chemical reactions fundamentally involve electron transfer or sharing between atoms. The availability and energy of electrons determines reactivity. The gap between the highest occupied and lowest unoccupied molecular orbitals determines how easily electrons can participate in reactions. In bulk gold, this gap is essentially zero, making electron transfer energetically unfavorable. But in gold nanoparticles, the gap opens up significantly, creating optimal conditions for electron transfer in catalytic reactions. Let's look at a real catalytic reaction. Carbon monoxide oxidation on gold nanoparticles. Gold nanoparticles catalyze the conversion of toxic carbon monoxide and oxygen into carbon dioxide. On bulk gold surfaces, this reaction proceeds at essentially zero rate at room temperature. But gold nanoparticles between 3 and 5 nanometers in diameter are highly active catalysts, even at minus 70 degrees Celsius. The molecules adsorb onto the gold nanoparticle surface, react, and the product desorbs, completing the catalytic cycle. The reaction rate on nanoparticles is roughly 1 million times faster than on bulk gold surfaces. The catalytic activity depends critically on the exact size of the nanoparticle. If gold particles are too small, below about 2 nanometers, they become structurally unstable and may aggregate. If they're too large, above about 10 nanometers, the The activity decreases as the particle approaches bulk-like properties. There's a sweet spot around 3 to 5 nanometers, where gold nanoparticles show maximum catalytic activity. Scientists use the D-band center model to predict and understand nanoparticle reactivity. Gold's d electrons play a crucial role in forming chemical bonds with adsorbed molecules. The D-band center is the average energy of the d electron states relative to the Fermi level. In nanoparticles, the D-band center shifts upward in energy, bringing it closer to the Fermi level and increasing reactivity. When the D-band center moves up in energy, molecules bind more strongly to the gold surface, facilitating catalytic reactions. Gold nanoparticle catalysts have important real-world applications. Gold nanoparticles can break down environmental pollutants like carbon monoxide, nitrogen oxides, and volatile organic compounds. Supported on porous materials, gold nanoparticles continuously convert toxic gases into harmless products. In the chemical industry, gold nanocatalysts enable selective oxidation reactions that produce valuable chemicals with high specificity. Gold nanoparticles improve fuel cell efficiency by catalyzing the oxygen reduction reaction at the cathode. Let's quantify the energy involved in these transformations. For CO oxidation on bulk gold, the activation energy is around 200 kilojoules per mole, making the reaction impossibly slow at room temperature. But on gold nanoparticles, the activation energy drops to about 20 kilojoules per mole, a tenfold reduction. The energy barrier for reaction on bulk gold is extremely high. But nanoparticles dramatically lower this barrier, making reaction rapid, even at low temperatures. This dramatic reduction in activation energy explains why nanoparticles are 1,000,000 times more active than bulk gold. Creating stable gold nanoparticles with the right size is challenging. Because surface atoms have higher energy, nanoparticles naturally want to stick together and form larger, less reactive particles. Gold has a surface energy of about 1.5 joules per square meter, driving this aggregation tendency. Without stabilization, gold nanoparticles quickly aggregate, losing their enhanced reactivity. Scientists solve this by coating nanoparticles with stabilizing molecules or depositing them on porous support materials. Protective ligands create a stabilizing shell around each nanoparticle, preventing aggregation while maintaining access for catalytic reactions. This super-reactivity phenomenon isn't unique to gold. Many normally inert metals like platinum, palladium, and silver become highly reactive at the nanoscale. Materials that are insulators in bulk form can become electrically conductive when reduced to nanoparticles. The same principles apply across many materials, opening up a vast landscape of nanoscale catalysis. Let's summarize the key scaling relationships that govern this behavior. Surface-to-volume ratio scales inversely with particle radius. Quantum confinement energy scales inversely with the square of particle size. Surface atoms scale with radius squared, while total atoms scale with radius cubed. Therefore, the fraction of surface atoms scales inversely with radius, just like the surface-to-volume ratio. All these key properties follow a 1/r scaling law, explaining why smaller is dramatically different. Let's understand this from a thermodynamic viewpoint. The change in Gibbs free energy equals enthalpy change minus temperature times entropy change. Surface atoms have higher enthalpy because they have fewer neighboring bonds, making them less stable. Each exposed surface atom adds roughly 30 kilojoules per mole to the system's enthalpy. This extra energy stored in surface atoms makes them thermodynamically favorable to participate in reactions that can lower their energy. The energy difference between stable bulk atoms and reactive surface atoms drives the enhanced catalytic activity. Gold nanoparticles represent a revolution in our understanding of materials chemistry. We've learned that size fundamentally matters. The same material can behave completely differently at the nanoscale. This transformation results from multiple factors working together: increased surface area, quantum confinement, reduced coordination numbers, and electronic structure changes. Understanding these principles opens up new possibilities for designing better catalysts, more efficient fuel cells, and cleaner environmental technologies. The nanoscale revolution transforms inert materials into powerful reactive agents, showcasing nature's elegant way of changing rules at different scales.